Now, continuing our discussion of partial fraction decomposition, there are two ways in which the problem can become more complicated. So, the first way is that you have a linear term that is repeated or appears to a power. And in this case, the denominators you have to put are not only the x plus a squared and the x plus b, but also any smaller powers of this x plus a. So, in our example, if we have an x plus a squared, I need it squared and alone. If I had x plus a cubed, I'd need a cubed, a squared, and an alone term. And then each of these simply gets a constant on top. Okay? And then we're going to solve it very similarly to when we had distinct linear terms. So, in our example, we want the partial fraction decomposition. Because of the squared term, I'm going to have one denominator with x plus 2 squared, one denominator with x plus 2, and one denominator with x minus 1. And all three of them are going to get a constant on top. Now, the next step is to clear the fractions by multiplying the entire thing by the denominator of the left-hand side. As will always happen, when I distribute this to the left-hand side, I'm just left with the numerator. When I multiply it by the first term here, the x plus 2 squareds cancel. I'm left with the a and the x minus 1. When I multiply it by the middle term, one of the x plus 2's cancel, and I'm left with the b, the other x plus 2, and the x minus 1. And when I multiply it by the last term, the x minus 1 cancels, and I'm left with the c and the x plus 2 squared. Now, I'm going to use the same procedure. First, I'm going to plug in negative 2, because that's going to make my first denominator 0. Okay. So, I get 9 equals a times negative 2 minus 1. This term is 0, and this term is 0, so we don't even need to write them. So this is 9 equals negative 3a, or a equals negative 3. Okay. Now, I try to figure out what will make my second denominator 0, but that's also negative 2. So since I've already done it, I can't do it again. The number that will make my third denominator 0 is 1, so I'm going to plug in x equals 1. I get 9 equals, this term is 0, this term is 0, and c times 1 plus 2 squared. So this is 9 equal 9c, or c equals 1. Well, now we have a problem. I've run out of things to plug in for x, and yet I still don't know what b is. So at this point, you just pick a random number for x that you have not already used. Now, I use negative 2 and 1. The next easiest number to plug in for x is x equals 0. So I'm going to plug in x equals 0 to be able to get b. I get 9 equals a times negative 1 plus b times 2 times negative 1 plus c times 2 squared. Now you say, well, how am I going to be able to solve this for b? Well, I already know what a and c are. So I get 9 equals a times negative 1 is 3 minus 2b plus c times 2 squared is 4. And now I can solve this for b. This tells me b equals negative 1. Okay. So the final answer to my problem is what I would get if I go back to here and replace the a with negative 3, the b with negative 1, and the c with 1. Now, I'm going to do another example that has a different problem for partial fraction decomposition. Okay. This one has a denominator that doesn't factor as much as you might like. So it's going to have a quadratic term that we call is irreducible, meaning it doesn't factor. In this case, just like you might expect, both factors of the denominator become denominators of the right-hand side. Okay. The difference is what the numerator will be. If the denominator is one of these unfactorable quadratics, the numerator has to be a linear term, ax plus b. This numerator would still just be a constant. Okay. So, let's do an example of one of these. Suppose we want the partial factor decomposition of this fraction. Okay. We see this x squared plus 2. It does not factor. Okay. So I know both factors are going to become a denominator. Okay. On top of this one, though, we need a full linear term. Well, just like with normal, the first step is to cancel the fractions by multiplying the entire equation by the denominator of the left-hand side. And just like always, when I multiply this out, the left-hand side is just reduced to the numerator. Now, here, the x squared plus 2's cancel. I'm left with the numerator times x minus 1. And notice I put parentheses around the numerator so that the whole thing will get multiplied by x minus 1. For my last term, the x minus 1's cancel, and I'm left with c times x squared plus 2. Now, I need to be able to plug in numbers to find a, b, and c. I want to plug in something that makes the first denominator 0. Only if you think about it for a little bit, you realize the first denominator is never 0. So let's skip that one. If I plug in x equals 1, it's going to make my second denominator 0. So, plugging in x equals 1, I see that this whole term is 0 because x minus 1 is 0. So I'm just left with the c term. Okay. This gives me that c is 4. Okay. Well, now we have a bit of a problem. I don't have anything else to plug in, and yet I need to plug in two different numbers, one to give me A and one to give me B. So, just like with last time, I decide, well, the next easiest number to plug in is 0. So, when I plug in 0, I get 13 equals B times negative 1 plus C times 2. And since I already know C, this is going to let me solve for B. So, this tells me that B is negative 5. Well, I still need to know what A is. So I need to pick another number to plug in. I plugged in 0 and 1. The next easiest number to plug in is negative 1. Okay, I plug it in, I get 1 plus 2 plus 13 equals, and you have to be a little bit careful here, minus A plus B times negative 2, and C times 1 plus 2. Okay. Be careful with the negative signs and make sure that you do your powers and parentheses appropriately. So this is 16 equals 2A minus 2B plus 3C. Now let's plug in what we know C and B to be. 16 equals 2A plus 10 plus 12. This tells me that A is negative 3. So, the final answer to my partial fraction decomposition is going back to here and plugging in A, B, and C. So remember, the two problems with partial fraction decomposition, if you have a repeated term, you need both powers as possible denominators. And if you have an irreducible quadratic, your numerator needs to be a linear term.